So before I describe the general principles of dynamic programming and general rules for when it applies, let's take a specific example. Suppose we have built a train line that passes through a number of towns. So the mathematical way to think of the train line and the number and the towns on it is to think of the towns at various integer points on a number line. So it's not that different, a train line and a number line. Now you want to place k stations. K is given to you. You want to place a certain number of stations on the line in such a manner that no town is too far from the nearest station. So basically, place k stations on a train line so as to minimize the maximum distance from a town to its nearest station. That's the problem we have. It's a little bit similar to the problem I mentioned earlier about hospitals in a city, but this is easier because we are working on a line. The train line is a nice one-dimensional object. So this diagram here shows you a solution with a cost of 1 for 2 stations to be placed on the towns, where the towns are located points 1, 3, 6, and 7. And you can see the station 1 is placed right in the middle of T1 and T2 at location 2. So the distance from station 1 to T1 is 1, and the distance from station 1 to T2 is also 1. And station 2 is placed halfway between T3 and T4 at location 6.5. So again, just to formalize this problem and to give it a mathematical representation, let's think of the towns as numbers, positive integers. So we're given a sequence of numbers T1, T2, up to Tn. These are the locations of the towns on the train line. The stations that we're going to figure out where to locate are going to be rational numbers. They may not be integers in general. They're going to be rational numbers S1, S2, up to Sk. And so basically, you're given T1 through Tn, and you want to find S1 through Sk. That's the challenge. Of course, note one thing about this problem. Once we've decided where to put the stations down, say someone has already told us station 1 is going here, station 2 is going here, and station k is going there. So suppose we've already made those decisions, then it's completely clear which station each town will use. Of course, each town will use the station that's closest to it. So what we have to decide then is, now we have to figure out where to place the stations. In particular, we always break down the question of where to place all the stations into little bits. We nibble away at the solution, and that's the general philosophy. So we ask ourselves, where should I place my leftmost station? The station furthest to the left on the number line. And to answer that question, we could ask ourselves another question, which is, how many towns is the leftmost station going to serve? So once you've decided the number of towns that the leftmost station is going to serve, the location of the station becomes very clear. Okay, so all we have to do is figure out how many towns the leftmost station is going to serve. Of course, we don't know the answer to that question because that depends on what it takes to handle the other towns, where to place the other stations. So these are all interlinked answers. But we know that there are only finitely many possibilities for the number of towns that the first station is going to serve. It's either going to serve just one town, the leftmost town, or it's going to serve 2 towns, the 2 leftmost towns, or it's going to serve I towns, the first I leftmost towns, or all n towns. So it's going to serve a certain number of towns, but we don't know how many yet. So what we will do is we will try all those possibilities. We will look at the position of the leftmost station so that it serves the first I towns for every possible I. This is the idea of dynamic programming. We ask ourselves a top-level question, where to place the leftmost station. We don't know the answer, so we will try every answer and see what it produces. So let's work through that. So again, if the first I towns use the leftmost station, in this example, the first 3 towns are using the leftmost station, but in general, it could be any I, then that station should be located exactly at the midpoint between the extreme towns that it's serving. So if it's T1 is the leftmost town, Ti is the rightmost town it's serving, then the station should be located at T1 plus Ti over 2. I hope you can convince yourself of this. It's not so hard to see, so I will leave it to you. So we have to use the remaining k minus 1 stations to serve the remaining towns, starting from I plus 1 all the way up to n. So what we can do, how we can compute the solution is using something called a recurrence. You've already seen recurrence relations when it comes to handling time complexity of algorithms, the time that algorithms take, but it's a slightly different kind of recurrence. So let me go through this a little bit. So locate ijl will find, is going to be a function, if you like, in Java, or method in Java, which will find the best location for L stations to serve towns Ti through Tj, and it'll return to you the maximum distance from any town to its nearest station. So this is going to be a function, and we're going to show how, for bigger arguments, this function can be computed using the answer to smaller arguments. That's going to be the recurrence relation. So again, let's look at locate ij of L, how to locate L stations to serve towns Ti through Tj. And we can ask ourselves that top level question. The first of those L stations is going to serve a certain number of towns, starting with Ti. It's going to serve some leftmost fraction of the towns. So let's say it's going to serve towns from Ti through Tx. So x is any town in the middle between I and j minus 1. Okay, here I'm assuming that we have at least 2 stations left to put in. So the first station is only going to serve at most all but the last town, because there's always a station available for the last town. Okay, so for some value of x between I and j minus 1, the first station is going to serve all the towns up from I to x. So therefore, the distance from the first station to the nearest town is going to be Tx minus Ti over 2. Let me show you that here. So this is the distance from the first station to the furthest town from it. So because the first station is serving all the towns Ti through Tx. And we're going to put that first station right in the middle of these towns, and so this is going to be the distance. Once we've done that, the remaining L minus 1 stations must serve all the towns starting from town x plus 1, Tx plus 1, to Tj. Because you have to serve all the remaining towns using the remaining L minus 1 stations. And so the overall solution to locating L stations between I and j is the minimum x you could choose, the minimum choice for the first station. And once you've chosen the first station, the maximum distance from a town to the nearest station is going to be either the distance to the first station, which is shown here, or the distance to some other station from some other town, which is captured by this entire term recursively. So this is the idea of a recurrence relation, because this idea works for k, if you have more than k stations, more than L is greater than equal to 2. So basically, if you've got 2 or more stations to place, you would reduce the problem of locating L stations to the problem of locating L minus 1 stations. And if you can keep doing that, we'll finally get down to the problem of locating 1 station, which is very easy to do, because if you have to locate 1 station to serve a certain set of towns, we know the answer already. We put the station right in the middle of those towns.